Hello, my name is Antonia Ettorre and I'm a member of the research team WIMIX in Area Sofia Antipolis. I am going to present our work entitled A Knowledge Graph Enhanced Learner Model to Predict Outcomes of Questions in the Medical Field. The focus of our work is the CIDES platform, that is, the National French Platform for Medical Studies. This platform is used by all the medical faculties in France to create and share questions and tests. And all the medical students can access it to train their knowledge and take official exams. Of course, the platform also registers all the learning traces of the students, that are all the records of the test they took and the answer they gave, with results and timestamps. Our work is collocated in the context of the transition towards a new version of the platform named CIDES 3.0. This new system aims to exploit the technologies and tools offered by semantic web and artificial intelligence to provide students with personalized learning services, such as personalized monitoring, augmented dashboard, and customized learning path. The first step towards CIDES 3.0 was the translation of the CIDES database describing all the university students and their learning traces into a knowledge graph version, named OntoSIDES. Starting from OntoSIDES, the final goal of our work is to be able to provide students with customized learning path, meaning that we want to suggest them with the best possible sequence of learning resources to improve their learning process. To do this, we need to know the current level of knowledge of the student and whether he or she will be able to answer the question we will present to them. So, the goal of this work is to try to predict the students' outcomes on medical questions. In other words, if they are going to answer correctly or not to such questions. In particular, we try to answer the following research questions. How to model students' learning on the CIDES platform, which set of features should be extracted from the OntoSIDES knowledge graph, and can, considering the knowledge graph structure, improve prediction results? Modeling students' learning is the goal of knowledge tracing. Indeed, knowledge tracing is the task of modeling students' knowledge acquisition to predict the results of future interaction with the learning material. Knowledge tracing has its roots in 1966 with classical test theory, and throughout the years several approaches have been developed, relying on logistic regression or Markov models, and some of them using parameters describing students' ability and question difficulty, some others wins and fails, and possibly involving also multiple skills. For our work, we decided to use one of the most recent approaches, the deep knowledge tracing machines. This model extends the previous knowledge tracing machine architecture by adding a deep component. We chose this model because of its flexibility. Indeed, it encompasses, as special cases, several less recent models, while allowing us to experiment with novel and heterogeneous set of features. A deep knowledge tracing machine is basically a neural network composed by two components: a factorization machine on the left of the picture, used to model pairwise interaction among features, and a deep neural network on the right to identify higher degree interaction. The input of a deep knowledge tracing machine is a one-oct vector encoding the feature. This is then transformed into the dense embedding to be fed to the hidden layer. Once we identify the model we want to use, we need to define the best feature to describe students in CIDES. To do this, we need to explore the OntoSIDES knowledge graph. This knowledge graph is quite huge, including more than 9.2 billion triples. But what we need to focus on are the answers. Each answer given by a student is identity related to its question through the property correspond to question, and to the student through the property done by. A question can also be of different types. In our study, we focused on QMA, that means multiple choice questions, and is also linked to medical specialty, and presents a text. It also has several choices for the answers, that are the instance of proposal of answers, and each one of these has its own text. Of course, the answers have also timestamp and the results that has a value between 1 or between 0 and 1, meaning if the answer was correct or not. And this is exactly the value that we want to predict. It is also interesting to point out that there are more than 500 million answers to almost 2 million questions given by more than 170,000 students. Based on this restriction of the graph, we identified four groups of features. The first group includes the feature extracted directly from OntoSIDES, like students and question ID and timestamps. The second group is composed by the features computed based on the previous ones and used to add a temporal dimension to our model. These are the attempts, the wins, the fails that summarize the number of times that a student sees a question, answers to it correctly or incorrectly. Question difficulty, static and progressive student ability. That is the ratio of correct answers given to a question or given by a student, either statically or temporally. The third group of feature is the text embedding of the question content. We extracted from the OntoSIDES graph the textual contents of the question and the introduction to it. That is the text of the evaluation grouping together all the questions related to the same case. So we applied the fast text implementation of Word2Vec to obtain the embeddings of this text of dimension d equal 300. The last type of feature that we wanted to consider are the graph embeddings of answers, question, and student. We extracted from OntoSIDES the nodes describing these entities with their neighborhoods, where each neighborhood is basically the set of the closest node considered to be most relevant for our task. We applied the node2vec algorithm to obtain vectors of dimension d equal 100 for each one of the nodes, and then we selected only the embeddings of answers, question, and students nodes. Once we defined all the possible features, we need to identify the best possible combination of them. We tested several models, including different sets of features, to analyze the impact of each one of them. From the very basic model, including only students and question IDs, from the most complex one, including all the features presented so far. So we tested our model on two different datasets. We chose to pick the learning traces of the students who took part into a national official exams in 2019. And among them, we selected a first subset of answers related to the medical specialty pediatrics and a second one related to the specialty cardiovascular. To train and test our model, in order to take into account the time dimension for our task, we decided to use a student-based temporal cross-validation technique. We consider our dataset as a set of the learning traces of multiple students, where the learning traces of a single student is a sequence of answers. So in this diagram, for example, each line is the learning traces of a different student, and each answer he gave is identified with a blue circle. So for the cross-validation process, we split the student into in our dataset into k folds. Then we pick the first fold and split it again, this time temporally, into two parts. Finally, we consider the latest answers as the test set while we train on all the other answers. So here we have that the blue circles are the answers used for training, while the red ones are the answers in the test set. We repeat the training and test process k time, each time changing the fold used for testing. So the results we show in this study are the average results obtained on all the 5 folds. So in this table, we can see the results that we got for the pediatric subgraph. We can see that the best model is the one including all the features presented so far, with an accuracy and AUC around 80%. When we compare these results with the one obtained with state-of-the-art features, so up to student ability, we see an improvement of about 5% for each metric, meaning that the use of text and graph embeddings gives a boost in terms of quality of the prediction. It is interesting to analyze also the behavior of two models containing only question graph embeddings and only student graph embeddings. We can see that these two models present a worsening of accuracy and AUC when compared to the basic model. Nevertheless, the best model, as said before, is the one containing all the graph embeddings together. This means that even though the single graph embeddings feature have a negative impact, the combination of all of them is very meaningful for our model. A last important factor to consider is the execution time needed to train our model. We can see that the best model presents an execution time of more than 14 minutes, while the second best model, that is the one without text embeddings, has an execution time of 8 minutes. So the time increases a lot when adding text embedding, while the difference in terms of accuracy and AUC is very small, less than 1%, as we can see. So we can state that finally, text embeddings do not bring enough improvement to justify such a steep increase of the execution time. So we repeated the experiments for the subgraph related to the cardiovascular questions, and we obtained coherent results. Even also in this case, the best model resulted to be the one including all the features, with an improvement when compared to the basic model of about 5% on all the metrics. We can also see that the behavior of question and students graph embeddings is the same as before. So we have a negative impact when they are used alone, but their interaction improves the prediction. And finally, we can see that also in this case, the execution time grows importantly when adding text embeddings, while the contribution to the quality of the prediction is even lower than before. So in conclusion, what we have done is to evaluate and compare several models based on deep knowledge tracing machine to predict student outcomes on questions in the medical field. We have identified the best set of features extracted from OntoSIDES knowledge graph, and we extended the state-of-the-art approaches, adding information coming from NLP techniques applied to textual content, and and also topological information coming directly from the OntoSIDES knowledge graph in the form of graph embeddings. And we have shown that these two new set of features are actually improving our prediction. So for the future, what we want to do is to evaluate our approach with other state-of-the-art representation algorithm. We want to exploit ontological knowledge contained in the graph. Indeed, so far what we have done was to use only the structure of the graph, but not the ontology. And we want to extend experimentation to other medical specialties in CIDES and to other knowledge graph containing the learning traces of students, even in different contexts. And for what concerns the CIDES project, what we want to achieve is to be able to design a recommender system that can provide students with customized learning path. Thank you for the attention.